So when students hear me say that math is a language, they often think, well, it's not like my English class, it's not like my French class. But make no mistake, mathematics truly is a language. What's really cool about math as a language, though, is that it's universal. We all speak math and read math the same way. It doesn't need any translation across the borders, if you will. So we talk about addition, subtraction, multiplication, division, or even as high as ideas in calculus, the derivative or the integral. We all mean mathematics to mean the same thing. So it's a universal language. Now, a lot of fields of study rely on mathematics to assist them, but no more so than physics. Physics relies so heavily on mathematics. The skills that are developed in the course, how do you solve equations, interpret equations, and so forth. It's often said, sometimes poetically, that the language of physics is mathematics, and that can be attributed to Galileo. He says the book of nature is written in the language of mathematics, and of course what he means by the book of nature here would be the physical world, how it works, how the world works. Now, like any poem I've ever tried to write, this statement needs some explanation. It certainly does not mean that math and physics are the same thing. So math is not physics, nor is physics just mathematics. Being good at one doesn't necessarily make you good at the other. Okay, they rely on very similar tools of the trade. Okay, we're going to work with equations quite a bit. We learn how to solve equations and so forth in a math course, but we have a different focus in a physics setting than we have in a math setting. The role of equations, how mathematics and how physics treat equations are a little bit different. A lot of the focus in a math course is how to solve equations. Okay, it's the skills, and these skills are certainly important in the study of mathematics. How do we solve a particular equation? What are these solutions? How do we obtain the solution from a quadratic equation or from a logarithmic equation, and so forth? There's a lot of techniques that are important to learn about how to solve. But what's more important in a physics setting is not the mechanics of the math. It's how we apply the mathematics. How do we use our knowledge of physical laws, these laws that are written in mathematical form with equations, how do we use them to be able to study the world around us? So it's knowing what laws to apply when, why they're applicable or maybe not applicable. It requires oftentimes a lot of problem solving and a lot of critical thinking to know even what laws to apply. So it's not about how to solve the equations, it's much more about how to apply the equations to our physical world. And of course the solution, a lot of times in our math classes, we're done. Once we get to a particular answer, we're done. In a physics class, oftentimes that answer is really just a starting point. Once we get an answer, that might lead us to maybe relook at the design to figure out if there's a way that we can change things so that we get a little bit different outcome. Physics equations describe what are called cause and effect relationships. They're not just generic relationships between X and Y. They're really a relationship between cause and effect. For example, if I push harder on the pedals of my bike, how much faster will my bike travel? The laws of physics can be used to describe that kind of relationship. They are very concise and very compact. They're very simple in nature. A lot of the laws that you'll see are very concisely, simply stated. But even though they're very simple laws, they are incredibly far-reaching, which means they have a huge range of application. Now, the solutions to physics equations do not just give us a value for X that makes some statement true. The solutions ultimately provide predictions. And so they're the predictions of a cause and effect relationship. Now, why predictions are so important is that one can then use the predictions to design solutions to particular problems that will meet particular goals. Now, ultimately, this is where physics becomes, the applied physics becomes a really important part of today's world. Engineering is essentially applied physics. So engineers rely on our knowledge of physical laws, the predictions that they provide. They rely on those laws to be able to make predictions that can then help steer particular solutions or particular solutions to our desired outcome. Okay. Now, engineering is more than just applied physics. They often have to deal with lots of other constraints besides just physical laws. So cost or safety or efficiency. They have to be pretty knowledgeable of a lot of different supporting fields of study. Ultimately, what engineers do is they try to reach an optimum design. Okay, they certainly have to work within the laws of physics to be able to create the design, but more than that, they have to be able to create designs that satisfy other needs as well. Okay, the language of physics is mathematics, a pretty profound statement, maybe a poetic statement. It certainly does not mean that math and physics are the same thing. They rely on very similar tools of trade, but with a different focus.